We spent a lot of time looking at graphs that are lines because we've been dealing with linear functions. Let's take a look at a few times when linear lines don't really match the scenario. So we're going to look at what's called the curve of best fit. So reading question 1, plankton and seaweed, which are the basis of ocean food chain, need sunlight to survive. As sunlight enters the ocean, it is absorbed and scattered by the water. The table and graph show how the amount of sunlight that penetrates clear tropical ocean water changes with depth. So we still have two variables. We have depth as our independent variable, and we have light as our dependent variable. We have the values in our table, and we can see we have this really interesting looking curve on our graph. We can still use our curve in order to read the points from it. Prediction 1. At a depth of 40 meters, so count over on your x-axis to the 40, read across, and our answer tells us that it's 30% of sunlight penetrates the water. Question number 2, at a depth of something, only about 5% of sunlight, so that's telling me I need to go to my graph on the y-axis, find the 5. Let's zoom in a little bit. So the 5 would be halfway to the first dash, read across, all the way over. So at approximately, I'd say that's 90. So at a depth of 90 meters, we've only got about 5% of sunlight penetrating the water. And then point 3, we're looking to find a depth of 10 meters. We want to figure out the percentage. So again, let's look over at our graph. Depth of 10, that's my x-axis of 10 all the way up. It's about halfway, so 60, 70, that'll give me about 75. So about 75% of sunlight penetrates the water. Let's look at example 2. We have an internet host as a computer directly connected to the internet. The number of internet hosts around the world has grown quickly. The data in the table are for January of each given year. So we have our different years. Up here, these are in the top. These are my independent variables. So years are going to go on my x-axis. The y-axis is our dependent variable, so that is our number of internet hosts. That's our y-axis. Number hosts. Let's plot our points. 1992, 0.7. 1994, 2.2. 1996, 9.5. 1998, we're now lifting up to 29.7, so that should be closer to just over the halfway mark. 2000, 72.4, so just about the halfway mark. 2002, we're at 147, so just under the 150 line. 2004, we're at 233. And to finish it off, 2006, we're at 395, which is just under, the 400 line. Okay, so we've dotted our points. We can see that it is clearly a curve and not a straight line. So do your best and connect the dots as curvy as you can. This is not easy on an iPad. And there's my curve of best fit. For question B, it wants to know what trend do we see in the graph and data. We see that it is increasing at an increasing rate. A straight line would be a constant rate, but because the jumps keep getting bigger and bigger and bigger and bigger, we would call that an increasing rate. Part C wants us to use our curve of best fit to estimate the number of internet hosts in 2001. So 2001, draw our line up, hit our curve, Read it across. Hopefully you're smoother than I am. And we're at approximately 120. So we're at 120. Don't forget our units. We're at 120 million. Our units should probably be on our graph here. Part D, when might the number of internet hosts reach 500 million? So now we're going to use extrapolation to solve for this one. So we're still going to use our curve, only this time we need to go outside our dots. 500 million, read across. I just adjusted my curve to make it match a bit better. Read straight down, and we're looking at 2004, 5, 6, somewhere partway through 2006. In the year 2006. Question number 3. The high divers at Canada's Wonderland perform competitive dives from a height of 21 meters. A diver's height is measured every 0.2 seconds, and the data is recorded in the table below. Before we even do anything, we can notice that we're starting with an initial height. So at time is equal to 0 is going to be our 21. And that is the point where it crosses our y-axis, right there. That's our initial point. I've already drawn the dots on my curve or on my graph, and I can see automatically that I have a curve. So a line would not fit best. I have now added my curve of best fit. That's the red line. Part B, what trend do you see in the graph data? So here we see that the trend is that the graph is decreasing at an increasing rate, or maybe at a faster rate, because we see that the dots are getting further and further apart as he goes down. C, when will the diver be 7 meters above the water? At 7 meters, this is going to be outside my point, so we will be extrapolating. So that means I'm going to use my curve to find a value outside my data points. Looking on your graph, 7 is approximately here, and I notice that it lands at about 1.6 seconds. Part D, when does the diver reach the water? That's the x-axis, because that's when my height is 0. And we can see that where my curve lands is right here at 1.9 seconds. Now your answer might be a little bit different because your curve might be a little bit different, but that's okay. We're estimating. Answers can be different. Question number 4 is asking for a line or a curve of best fit for each scatter plot. For my first one, the calories burned when walking, I can see that my dots make a very nice line, so I have a very strong correlation. So I now have my line of best fit for the graph, the first graph. The second graph, Ontario's population, we see actually is a bit more of an S curve. Good luck drawing yours. Do the best to follow the trend. And you should end up with something that looks similar to that. Okay, now it's time to predict some values. So part A, about how many calories does a 55 kilogram woman burn when she walks for 30 minutes? So let's go to 30 minutes, read up, and remember we're reading off of our line, not necessarily our dot. And I would read that to be at approximately 130 calories. About how long does a 55 kilogram woman need to walk in order to burn 200 calories? So again, let's look at our graph. This time we're going with 200 calories. 200 calories, let's read down, and we are looking at 42 minutes. Okay, time to predict the approximate population of Ontario in 1945. So we go to 1940, there's 1950, so 1945 would be here. Read across. About 4 million. Good, and last but not least, in which year was the population of Ontario approximately 11 million? So let's take our graph, 8, 9, 10, 11 million. Now read down to finish reading the graph, and we are looking at 1980, 1990, 1995. And there you have it. That's using our lines of best fit, our curves of best fit, interpolating and extrapolating to find values. Well done.